All right, good afternoon. I'm Adam Tucker. I'm a chain dev at Osmosis Labs, and today I'm going to be talking about chain profiling and improving chain performance. To give you guys a little bit of a background, this started about 6 months ago. Dave from the Osmosis team and I decided to try and answer one question, and that question was, why is Osmosis syncing so slowly? And that devolved into not only answering that question, but learning a lot of different information as well. So we both agreed that sharing this DEVMOS would be really important. And so that's what we're doing here. The goal here is that at the end of this, if you're brand new to profiling, you'll have everything that you need to at least start profiling your own chain, and then eventually being able to contribute to the stack that we share as a whole. So what we're going to be talking about here is first, how do we measure performance? There's just going to be a couple of ways that we measure it personally. Next, we're going to be going into the types of profiles. Just very briefly, if you've never seen a pre-prof before, it's going to be a couple minutes. But it's just going to be enough for you to tag along. Then the meat of the presentation is going to be these 3 examples. And my goal with these 3 examples is to really convince you that if you were given this exact information and enough time, and you're a chain dev, that you would have been able to come to the exact same conclusions that we did. It's nothing crazy. I mean, some of them were a little bit in the weeds, but the majority of them are very obvious issues that all that we needed was the actual data. And this is how we got it. And then after that, we're going to be going over, what's next. Now that you have this data, what can you do with that to take Cosmos profiling to the next level? So for the first way that we measure performance is through sync speed. What is sync speed? It's when you're not at the head of the chain yet and you're syncing up, how many blocks per second is being synced. We believe that at a very minimum, the sync speed should be 10 times the block production rate. Where did we get this number? It's kind of a function of 2 things. The function isn't perfect, but it'll get you in a ballpark for your own chain. At the numerator, we have the interval at which snapshots are taken in hours. So for Osmosis, we give a snapshot every hour. And the denominator is what's the maximum amount of time that you want to take to reach the head of the chain. And so we said 6 minutes sounds about right. So that's where we got 10. And so where were we before? So 6 months ago, we were at 0.8 blocks per second. It was extremely slow. That was 4 times the block production rate. And if we were to have kept the same block speed or block time of 5 seconds, we would actually be at 40 times the block production rate today. We decided that we would reduce the block time because of all this performance stuff. But yeah, it's still at 20 times, which is significantly better, 8 blocks per second. The next way that we measure performance is through the network average signed. What is this? That is the average amount of blocks that our validators sign. Obviously, there's going to be a lot of things that are out of our control, like maybe validators have bad internet, bad hardware. But what's really important for you all is when you do a upgrade, you look at, are we trending upwards, or are we trending downwards? Because if we're trending downwards after an upgrade, it tends to mean that we introduce some non-performant code, and we should do something about it. And the last way, and I say last way, there's many different ways to measure it, but the ways that we did was block processing time. So block processing time is consists of 3 different things. One is the time to execute the block, so how long it takes to actually run the transactions in the block, run the begin blocker, end blocker, etc. The next is the time to gossip and vote on that block. So if a block is larger, it's going to have many more block parts. And so those block parts need to get propagated to the network and voted on once it becomes a block. And you'll notice that some networks that are more centralized on the network will be able to gossip this quicker. Others that are more decentralized will be able to gossip this less fast. And then lastly, we have the timeout commit, which is the validator. They just set this timeout value, and it's how long they wait after committing a block to start on the next block. So that's what block processing time is. These are the 3 main ways that we actually measure performance. Yes? Oh my gosh. I am so sorry. Well, there you go. Thank you for that. This was the block processing time slide, and we'll go on to the next one. Sorry about that. So what's the strategy? The strategy is the purpose of profiling. So the quote that I have here that I liked a lot was, the purpose of profiling is not to find where the code is slow. The purpose of profiling is to find where the code is doing something unnecessary. And so you'll hear me during this presentation talk a lot about does this make sense? We're not really looking, sometimes when we're profiling, we want to look at the largest amount of process that a function is using. But a lot of the times what we really want to do is just look and say, does this make sense? So you're going to hear me say that a lot throughout the presentation. Really quick on pprofs, there's many different types of pprofs. We're only going to be going over 2. I think there's like 7, but these are the 2 main ones that we use when actually finding all these issues. First one is CPU, that's the amount of time spent in each function call, and the next is the heap, so the amount of memory allocated to each function call. I'm sure a lot of you are familiar with this screen. This is the config.toml, every chain has one. So yeah, woo, okay. The way that you set it up is you set the pprof listening address to a non-blank string. We have localhost 6060, and that's all you need to do to set up the pprof. It's literally that easy. And the last thing I'll do when I'm talking about, just to get you onboarded onto what pprofs are, is go over the flame graph view. There's also many different types of views, but this was the one that we used the most to actually like understand what was going on. So you'll see a lot of rectangles. The wider the rectangle is, the more resources that are used for that function. The function will be in the rectangle. There'll be a top level function, which is what you click on, and you'll see either the amount of time spent in that function or the amount of memory allocated to that function. And then last thing you need to know about flame graphs is when there's so your verify signature at the top, everything underneath that block, that function was calling. So that means that whenever you see a top level that's stacked on others, that function is calling other functions. I might have gone a little fast on it. If you're not following, when you go over the first example, it'll probably set in a little bit better. So the first example is an event-oriented memory profile. What this means by event-oriented is something bad happened and we want to figure out what happened. It's very specific. So in this, we had an upgrade, and then we all of a sudden our gRPC, our RPC nodes that are being served to the public started going OOM. They crashed, and we had no idea why. This node was like 6 times in the event of 24 hours. So there's 2 things we could have done. Thing 1, look at the timestamp and then go over the tens of thousands of queries that happened during that timestamp and try to figure it out that way. Or we could run a memory profile and figure it out that way. So that's what we did. There's 2 ways that you can run a memory profile. My recommendation to you all is if the issue is happening right now, do option 1, because you can set it for 30 seconds and then you'll have to sort through a lot less information. If you're not lucky and it's happened just sometime in the lifetime of the application, you're going to have to do option 2, but you'll still be able to get to the answer. So I'll show option 2 because there's a little bit more noise, but you'll see at the very top, over an hour period, we allocated 3 terabytes of memory, which sounds wrong, right? Probably something bad is happening here. But in this example, we want to see what was using the most memory. This is the one example where we actually want to see what's using a lot. And so I'll highlight here this registered gRPC server function. It's the widest block, and we want to click into it to see kind of what's going on. So we click into it, and we see at the top, 48% of the memory was being allocated to this. And we see in the top right here, query validator delegation. We see some kind of IBC query. We see some kind of gov query. But obviously, the one on the left here is utilizing the most. So we're going to click into that. This get TX's event, and we see that 35% or 1 terabyte of memory is being used in this TX search function. This is, I'll kind of spoil it for you. If you were to highlight over it, you'd see that TX search function is in Comet. You look at the code, and I'll just really quickly go over what was happening. First, we get all the events across all available heights. So imagine we're searching for a bank send event. We then sort all the events across every height, and then we paginate, and then we discard the results that we didn't use. So why not just search for what we're actually going to return? So I linked the PR in the bottom right of what the actual answer was, because it's a little bit more involved. But you also see a comment here, sort results must be done before pagination, which was just false. So it's kind of like, was kind of taking you in the wrong direction initially, which is probably why this happened. Next, we'll go over a sync profile. What I mean by sync profile is the node isn't at the head of the chain yet, and we're taking the profile while that's happening. This is going to be a CPU profile. So it's almost the same command as before. And like I said, at the top, you'll see a time, and this is going to be over a 5-minute period of time. This time, we're not actually looking for something specific, right? Before we knew kind of what we were looking for, and now we don't. So what you would normally be doing is you'd kind of be clicking through all these boxes to just kind of see and ask yourself, is what's happening making sense? So I'm going to kind of take you to the answer, but like obviously you wouldn't know to go down this path. And there's probably multiple other issues in this as well, but like let me take you down one. Okay. I'm going to have to go a little bit faster here. So we go down this execute contract, and we go down this swap exact amount in, and we see here at the top that swap exact amount in is taking 1.2% of our sync time. And so that could make sense. Maybe we have a lot of swap events, but if we go down one block, we see that half of the swap exact amount in time is being taken on charge taker fees. And that should just be a multiplication operation and a send. So let's figure out what's going on. We click into it. And we see that almost 75% of the time of our taker fee is being taken in tracking. So we definitely, that doesn't make sense. So let's look at the crappy code. I can call it crappy code because I wrote it. But I'll just like spoil it for you here, is what we were doing was, this is a common foot gun, at least common for me because I've made the mistake multiple times, is that we have a key and the value is an array of coins. Let's say we charge 1 USDC of taker fees. And then what we do is retrieve the byte array of all the coins. We unmarshal all those coins. And then we add just 1 coin to those coins. And then we restore them. So what we did was we unmarshaled all those coins for no reason. All we needed was the USDC coin. So what the correct answer on a micro level of what we could have done was we could have actually just keyed it by denom. So all we're doing is we're querying for this key. We have an int, and then unmarshaling an int is much easier than unmarshaling coins and more performant rather. I have to go really fast, so I'm gonna try to. So this store.write, if you were to go into it, you'd see all these sets and 15% of the sync time being taken here. But the problem with pprofs is you actually can't tell what's being set and deleted. But what we did was this really hacky thing, and that was kind of cool, was we added these print lines. I'm not going to go into it because I don't have time. But what we were able to do was those print lines were able to create all the writes of each height. We fed it into ChatGPT, got a CSV, and then we were able to just chart this out. And we see at a glance here that distribution module is doing more writes on multiple magnitudes than every other module. We wouldn't have known to look at this without the pprof. So if you were to look into the distribution module, what's happening is, and again, does it make sense? It actually does for some chains. For some chains, you actually pay the block proposer differently than you pay the other validators. But for Osmosis, we pay all the validators the same, whether they propose the block or not. So we were able to distribute the block rewards every 50 blocks instead of every block. So that's 50 times less write now. And we wouldn't have known to do that without the pprof. So last example, a head profile. This means that you're at the head of the chain, taking the profile. This is over a 25-minute period. You'll see this green column. It won't be green for you sometimes. The colors are kind of picked randomly. But this green column here wouldn't have been visible during a sync profile because you're not doing these operations until you're at the head of the chain. So that's why it's important to do a head and a sync profile. We click into this. We click into commit. And we see something, and I said on the bottom right, it was like, this is hard. The reason why this is hard when I click into this mempool update function is if you don't know like very much about the stack, you wouldn't know that anything's wrong is really happening here. But what's happening is, I wanted to point this out because of how important it is that you'll see that the mempool update is below commit. That means that mempool update is blocking commit. And it's hard because you don't know that this is not necessary. We actually don't need to block commit on updating the mempool. So there was a PR on the left. You see mempool update under commit. That means it's blocking. On the right, after the update, it's its own go function where update is under async update mempool. So what's next? This is almost my last slide here. What can you all do with this information to help improve the stack? Well, there's a couple things. One, everything that I showed you right now was state compatible. It was very easy to test. We were able to sync it against mainnet and check it this way. But there's plenty of things that we can do that aren't state compatible that we still need to test. We have this thing called in-place testnet. You're able to spin up a mainnet state testnet instantly. But what we don't have is something that can actually spam real transactions against that testnet. So if you're interested in building this, please talk to me afterwards, and I can explain like what would be great for that. Next thing that you can do, if you take nothing out of this whatsoever, just profile your own chain once. You'll actually learn more about your chain this way than you'll ever had before. And once you do that and you start becoming comfortable, I recommend eventually making improvements to Comet, IBC, and the SDK, because this is all what we all share. Last point here is automated regression testing. We don't have a baseline across all chains, so we don't really know when we're introducing a feature. Maybe Skip introduces a feature. They have no way of knowing, does this make the chain perform worse or better? So having that baseline is very important. This is the last slide. Everything I just talked about, the slide deck, the pprof examples, the code to actually wire in that in-place testnet if you're interested, as well as auto pprof. What we made is GitHub action that actually profiles all the code automatically. It's not a plug and play. You're going to have to do your own thing, but still, I think it might be useful for you all. If you have any questions, I probably don't have the time for it, so either talk to me after this or hit my GitHub up, my Twitter's on there. Thank you all so much for your time. I appreciate it.